Okay, so the last talk for today on this track is from David Burgess on IMSI catchers in 2021. I think.
Actually,
Sorry.
it's actually proactive SIMs. We changed it at the
Okay.
last. We
Okay.
changed it yesterday as
Sorry.
active proactive SIMs. Thanks. Okay. All right. Okay. So again, my name's David Burgess. There's my contact information. Thank you for being here for the talk. Subject of this talk is proactive SIMs. They're not necessarily directly a security threat, but they're an interesting possible attack vector. And we're going to talk about that. I'm going to start out sort of a joke of mine at this point. Telecom is not IT. The purpose of telecom networks is very different from networks that you'd see in the IT world. Typically, you'd say that the purpose of an ISP is to provide connectivity between IP devices, but the purpose of a mobile network is to generate invoices. And everything that a mobile network does is a side effect of its process of generating invoices. And everything you're about to see in proactive SIMs are there to provide, to allow mobile operators to provide billable services to their customers or to provide ways of differentiating themselves in the market. And that drives a lot of what happens in the telecom industry. And this, especially in more recent years, as mobile operators sort of struggle to maintain relevancy and not just be dumb data pipes, it's sort of causing a kind of breakdown of the security models that the telecommunications networks were based on for decades. And again, unlike IT, this is an industry that goes back over 100 years. They've been building networks for a very long time. So these are the components of a typical mobile network. This is to give some context to what we're going to talk about in a few minutes. We have I can do this. We have the core network. The core network is basically where all the things you think of as the service of the mobile operator, it's where they actually happen, is in the core network. Or to some degree, they happen in the SIM. The radio access network is really just a sort of transport mechanism that connects terminals to the core network. And in the telecom world, the assumptions of the terminals are pretty dumb. They want the terminals to be dumb. They want all the intelligence to be in the network where they control it. But as we're going to see, some of that intelligence got moved into the SIM. If we look inside the core network, this is a circuit switch core network that you would see in a 2G or a telephone call handling part of a 3G network. There's deep in the heart of the network is something called the home location register, the HLR. This is the master subscriber database. Everything that the mobile operator knows about you is either stored in the HLR or indexed through the HLR. And everything of significance that's in your SIM is also in the HLR. Then we jump forward to 5G. There's a component called the home subscriber server. It's basically the same thing as an HLR. It's just it has a diameter interface added to it. Although in practice, SS7 is still around because diameter roaming is still not fully standardized and still not the standard common practice among mobile operators. So the SS7 network is still there, it's still relevant, and even though the HSS may talk diameter to other parts of its own local core network, when it talks to other operators, chances are it's talking SS7. This is an even more simplified high-level view of a mobile network. Especially during security procedures, it's basically the SIM talking to the HLR. And everything else is really just a transport mechanism between the SIM and the HLR. And then the all-important billing system, which gives the whole network a reason to exist. So now we sort of establish this kind of framework. Let's talk about SIMs. I have plenty of time. I can slow down a little bit. So the SIM is really a complete computer system. And there are, in your typical, this is a model of a typical smartphone. And it actually has 3 computers in it, and each one has its own operating system and its own APIs. And the application processor is a thing that's running Android or iOS. From the point of view of the telecom world, the application processor is a kind of added-on accessory. It's not really part of the phone. And it's sort of a circus of dubious third-party applications that should never be trusted under any circumstances. Below that, we have the baseband processor, which is a thing that actually manages the telecom, that actually runs the telecom functions of the phone, communicates with the cellular network, and then below that you have the SIM. And when you plug the SIM into the phone, it engages very closely with the baseband processor. And if you look at this architecture, you can see that it's entirely possible for the SIM to use the baseband processor to communicate with the cellular network, and the application processor, Android, iOS, whatever, has no idea what's going on. Will never have any idea what's going on. So what's a SIM? SIM starts out as the standard old ISO 7816 smart card. Oh, I have a monitor right there. And what's in there? Well, there's a CPU. It's usually a 16-bit CPU. It's running its own operating system. It has a few kilobytes of RAM. It might have a few tens of kilobytes or even 100 kilobytes of backing store in a file system. This operating system has different security classes. It has different, multiple security classes and groups. Different files and different functions can have different access privileges for different security classes. So, for example, if we want to write the secret key K of I into the SIM card so it's not accessible by anybody but the mobile, so it's not accessible and readable, that K of I is simply written into a file that has write-only permissions for anyone except maybe a certain security class. It's only used by certain applications inside the SIM card. And from that point on, the K of I is its secret. It's stored in the SIM. Nobody's going to see it. So about half of all the smart cards that are ever made these days are SIMs. The SIM market is dominated by two companies, Gemalto, which is a Dutch company that has about half the market, and Oberthor, which is a French company, which has about 25% of the market, and the other quarter is small scraps. Above the ISO smart card API, there's another API that's provided that was defined by 3GPP, by ETSI, called the SIM Application Toolkit. It's a standardized extensions that sit above the original smart card API that provide functions specific to cellular operations. And this API allows the SIM to do things like access the keyboard and screen on the application processor. So a lot of times if you use, well, in this case, the applications, the SIM might be used for subscriber account management, so you can like *123#. And when you do that, what you've actually done is you've engaged an application inside the SIM. And what you're interacting with in an example like this, you're actually interacting with a SIM, not with your application processor. And then another layer of software is put on top of this. Nearly all the cards in the market today have Java virtual machines built into their operating systems. And this allows what we call applets, Java applets that can be deployed onto SIM cards. So the question is, why did it end up like this? How did the SIM card end up being such a sophisticated computer? And the reason it ended up like this is because the SIM cards were first conceived when all these features were added to SIM cards. It was before the day of smart cards. So you had a feature phone. The feature phone really didn't have much of a computer in it. It might have a little microcontroller that managed a 12-key keypad and a little LCD display. And all the other functions of the smartphone were actually in the SIM provided by the operator by Java applets that were either pre-programmed to the SIM or loaded over the air through SMS. So even today in poorer parts of the world where smartphones are still not common, the SIM is the computer that people have. That's their main experience of computing is interacting with SIMs. That's the computer they own, is their SIM card. So, quick example of SIM operation. Step 1 and step 2 in this thing may be months apart. The card issuer will write the K of I, the magic master secret key that's supposed to exist only in the SIM and the HLR. That's the basis for all security and authentication mechanisms in the mobile network. The SIM CPU will write that into the file system, and then that file will become that file becomes basically invisible to all but the most privileged application running inside the SIM. Then later, in order to perform an authentication procedure, it does a challenge response authentication. A random number provided by the HLR goes to the SIM card. The SIM card hashes that random number with KI using some security algorithm and returns a value called SRES, and then SRES is returned back to the network and compared against a corresponding result back in the network. That's how you authenticate. That's how you authenticate phones. But now we're going to talk about proactive SIMs. The ISO smart card standard makes a smart card a slave device. So by the standard, smart cards can't initiate operations. So how are you going to make a proactive SIM? You define in the standard that when the baseband processor boots up the SIM, one of the things it does is it asks the SIM, hey, do you want to do proactive stuff? And the SIM says, yes, I want to do proactive stuff. Poll me every 15 seconds and ask me what I want you to do. So then the SIM and the baseband processor get into this little dance where every 15 or 30 seconds, the baseband processor says, SIM, do I do anything? And the SIM, nah, not yet. Do I do anything? Not yet, not yet. And then eventually the SIM might tell the baseband processor to do something. In this case, we're going to say the SIM tells the baseband processor to send an SMS to a particular address through a particular SMSC. And the baseband processor does it and reports back success. Or it could say, SIM card, do you want me to do anything? And the SIM card could say, yes, put a pop-up window on the display. So the baseband processor talks to the application processor and you get the pop-up window. So what can proactive SIMs do? Three basic things a proactive SIM can do. It can register for event notifications with a baseband processor. So it can detect service changes, like if you move from one network technology to another, or if you lose service, if you regain service. It can be notified of location updates, so if your phone moves from one geographic area in the network to another and has to register again with the network, the SIM will receive a notification of this. It can set periodic timers, like the 15-second, 30-second polling timer. It can set one-shot timers that just says, hey, baseband processor, come back in 5 minutes and ask me what to do. It can detect call events, SMS events, anything that you do that creates an interaction with the mobile network, the SIM can get a notification of this. It can also detect if the phone goes to sleep. So if your phone goes to sleep and the lock screen comes up, or when you unlock it to start using it again, the SIM can get a notification of this. Second set of things that the SIM can do is request information. And there's the list. It's pretty good. It's pretty good. It can go as far as getting your GPS location. In more recent versions of the API, it can actually request GPS location from the baseband processor. And also time in advance and neighbor measurements. This is information that can also be used to geolocate a phone in a network. If you have enough information about the geographic structure of the network, which you can get publicly from websites like cellmapper.org, you can use time in advance and neighbor measurements to estimate the location of the phone also. And then what can the phone do? It can communicate. It can also communicate. And what else does the SIM do? It'll communicate. It can send SMS. It can initiate USSD operations. USSD is a protocol that uses packets similar to SMS, but it's not store and forward. It's a connected real-time protocol with very low latency. It can open TCP/IP data sessions. It can send and receive UDP datagrams. It can start telephone calls. It can send arbitrary AT commands to the baseband processor, and it can even tell the application processor to launch a web browser. And other than the browser request, all this is completely invisible to Android or iOS or whoever the ringmaster is in the circus up there at the top. So my first exposure to proactive SIMs was actually just earlier this year. It was actually in 2008, but I didn't know it. In early mid-2008, I was writing OpenBTS, something called OpenBTS, which is a GSM stack, a GSM stack that runs into Unix. And I was writing OpenBTS, and it was just starting to work. I said, what's something fun I can do with OpenBTS? I know, I'm going to get some prepaid phones. Just go buy some cheap prepaid phones, run them under OpenBTS, under fake networks, and just see what they do. And one of them was something called an AT&T Go phone, which is a really cheap Nokia phone with a prepaid SIM. I go get my AT&T Go phone. I spoof AT&T with OpenBTS. I fire it up, and the first thing the Go phone does is send a text message to this number. And I think this is interesting. I wrote a little blog about it at the time. There was some discussion, some comments, and that went on, a few days of fun on the blog, and that was it. Okay, fine. Then in February of this year, a paralegal called me from a law office in the United States and said, hey, what do you know about text messages to these numbers? I didn't remember all this. She said, no, really, I found a blog where you wrote about this. What do you know about it? I said, well, I'll have to go back and read the blog to remember what I know about it. She said, okay, here's the situation. We have a wrongful death case. A young man got into a traffic accident near a construction site. The family's suing the construction company, and they're suing the highway department who hired the construction company because the area was not properly marked, the traffic wasn't properly managed. This was an avoidable death if they just followed the procedures. But the defense in this case ordered the cell phone logs for this person, for this driver, and found in the cell phone logs a text message that came out of his phone really just seconds before the accident. And the defense is arguing this is a case of distracted driving, that they're not at fault. The reason this accident happens is because the guy was playing with his phone. And they said, can we hire you as an expert? I said, yes, sure, let's do this. So here was the approach. First thing we did was we built an SMS, we built a test bench for testing these SIMs. And his particular SIM, the attorney didn't want to give it up, but it just so happens that they could find a SIM that had a very similar ICC ID number that probably came from the same batch. It was probably ordered and issued by AT&T around the same time, probably identical firmware in it. So step one is we form a hypothesis, and step two is we go subpoena AT&T to verify our hypothesis. And one of the interesting things about working with attorneys is you don't just have to reverse engineer in the blind, you can actually get the attorney to demand answers from people, which is fun. So the best tool in here is something called SimTrace2. This is a device, you can see here the SIM plugs in here, and there's a flat cable that comes out of SimTrace2 that goes into the SIM card of the phone, and now SimTrace2 sits between the SIM and the phone, and you can monitor the traffic. And the hardest part of using SimTrace2 is you have to take a file and cut the SIM trace so that the cable fits. This is a fine product of the good people at Sysmocom, so go order one. This is the full test bench. Over here we have the SimTrace2 and the SIM. We have the phone, and on the other side we have a network emulator that's run on YATE-BTS, something called YATE-BTS, which is a more recent update of OpenBTS. And these both send PCAP files, and we get them into Wireshark, and we see what's happening. So the procedure is, we configure the YATE-BTS to mimic AT&T using the AT&T GSM network, using the network at PLMN country code 310, network code 410. We put the SIM in the trace tool, we power up the phone, and then we watch Wireshark filtering for SMS until we see something happen, and then we go back and look more closely. So what did we get? Well, we saw the SIM set up when we go back and look in the Wireshark, what do we see? We see the SIM configure proactive polling. The SIM makes repeated requests for the IME ISV from the host phone. And after a few seconds of this, the SIM tells the baseband processor to send an SMS. And maybe a second later, that SMS arrives in our network emulator, and we can check the content. It is, in fact, the same SMS. Quick side note, what's an SMSC? An SMSC is a store and forward server for SMS. You can think of it as being kind of like an email server. So when user A sends SMS to user B, it's going to go through an SMSC somewhere. That SMSC is usually, it's indicated by user A's SIM or by user A's phone when the message is sent. It's usually an SMSC that was programmed into the SIM, into user A's SIM by user A's home network operator. So what's the message content we found in this case? The message, again, was sent to this strange-looking number. By the way, this number does not fit into any public numbering plan, this 111134002. It doesn't fit into any public network numbering plan. This is not a number. This is not a telephone number in the real world. It's not an E164 address anywhere in the real world. This is a private address, which means it has to be handled by specifically by an SMSC that knows how to route it, because it's not part of any public routing plan. And that SMSC is +1 404 752 9800, and I'll talk about that number in just a minute. Here's the content of the message. The blue is the content, and what it is a binary format SMS. It uses what's called a TLV encoding, which is very common in telecom protocols. Type, length, value. The first byte is a type code that identifies the field type. The second byte is a length that tells you how many bytes are in the field, and then the value, which is the length L. This message encoded the IMEI-SV of the phone that the SIM is currently installed in, the IMEI-SV of the SIM the phone was previously installed in, which means it was storing the IMEI-SV in its file system between uses, and then the IMSI of the SIM and the network information and the cell ID and something called the terminal profile, which tells what features this particular phone supports. Now, I don't fault AT&T for this. This is useful information. If you're a mobile operator who has to support, you want to make sure that features work on lots of different models phones for all your customers. This is useful information. This has a legitimate business purpose. I'm not saying there's something sinister about this, but it's, unless you happen to be the guy with a bad entry on your phone records in the middle of a lawsuit. Yellow, this thing in yellow is the routing, what's called the relay layer routing header for this text message, and it identifies this number as the SMSC that's supposed to be used for carrying this message. So this SMSC is not the normal SMSC that AT&T uses for text messaging. If you send normal SMS from one person to another, it does not use this SMSC. It uses something else. So what is this? I'm sorry this looks so plain. I had a software problem with actually, copying an image out of a PDF file, so this is just the text from a PDF file. This information comes from something that's called an IR21 file, an IR21 form. IR21 is a standard form that's used by members of the GSMA, which is like the global industry consortium for mobile operators. The IR21 is used for reporting technical details of roaming interconnections between mobile operators. So when two mobile operators want to establish a roaming connection, they exchange a lot of documents. But the primary technical document they exchange is something called the IR21. And the IR21 lists all the publicly exposed interfaces of the mobile operator. And this particular document for AT&T was about 50 pages long. But it lists all the publicly exposed interfaces. It lists all the functions that are provided behind these interfaces, and it gives contact information for actual real living people who are responsible for making these interconnects happen. It gives their names and their telephone numbers and what city they're in. This is an operational document that people actually use to make things work. But when we go through here, we find this entry. There's our magic number. And what these columns mean, it's an SCP, which is what's called a service control point, which in the SS7 network means it's a kind of server of some sort. It's not a router, it's a server. There's the number. The vendor for this equipment was Sun. And do I believe that like this document was from 2020, do I believe in 2020 that AT&T still has a Sun Solaris server somewhere in the guts of their core network? Absolutely. You see a bunch of other ones up here? Because one of the rules in telecom is if it ain't broke, don't fix it. So there it is. It's a Sun Solaris server. It's probably running an Oracle SMSC package. Okay, so now we have enough information. We know where this server is. It's actually, physically, this machine is on the outskirts of Atlanta, Georgia, in the suburbs of Atlanta, Georgia. We have contact information from the R21 form. We know who runs it. We actually have names of people. And so the attorney sends a subpoena, demanding documents or witnesses to explain what this SCP is used for. AT&T was a little surprised by this request, by the specificity of this request. They spent a month trying to avoid the subpoena, offering different things that weren't very useful, but eventually they produced a witness. This witness referred to that particular SMS as a service change message. He confirmed it was triggered by an iOS update that had happened on the phone earlier that morning, that it resulted in an update of the firmware on the baseband processor, and also confirmed that this SMS was not related to any particular actions of the user. It just happened to be sent at that time because the firmware update on the baseband processor had just completed around that time. It had nothing to do with the user. So, this is my first experience with proactive SMS, but I thought it was really interesting. So the next thing I did was take all the other SIMs I had laying around and run them through the same system and see what I found. T-Mobile USA sends some sort of ASCII payload SMS. It's obviously some sort of machine-to-machine message. I don't know the purpose. It sends this whenever the phone is first started. The first time it gets a network connection after a power cycle, it contacts T-Mobile and sends this SMS. I don't know its purpose. Orange Romania does something very similar to AT&T. They send a message very similar to the AT&T message, but I thought the most interesting was Verizon. I give one example over here. One example over here of the content of one of these SMSs. I mean, not the content of the SMS, but the content of one of the PDUs being exchanged between the SIM card and the baseband processor. And this is commanding the baseband processor to open a data channel, and it is a TCP channel. It's demanding that it opens a TCP IP channel on port 8443, and depending on the version of the SIM, there may be different IP addresses here, but they're all IP addresses that are publicly, according to WHOIS, these IP addresses are always owned by Verizon, but they don't route in the public internet. One of the clues here is, oh my goodness, what did I do, folks? Sorry? Okay. One of the clues here is this access point name, VZW admin. When cell phones establish data connection, when they establish data sessions into the core network, these data sessions are established in contexts called access points, APNs, access point names. But within any access point, there are different routing rules. You'll usually have one access point that'll be called something like internet that actually routes to the public internet in the way that you would expect. But there are other access points that may follow different routing rules. For example, if your phone supports IMS, there'll be a different access point for IMS that does not route to the public internet. It routes to a private isolated network inside the core network because they don't want to expose their IMS to the wilds of the public internet. So this particular access point name is VZW admin, and it seems that these addresses mean something different in that access point than they do in the real world. So the next time I'm in the United States, I'm going to try the SimTrace 2 and see what I get. But here in Europe, I don't get anything. So I thought that was one of the more interesting ones. But sometimes, so here we are. Why do we care? why do we care? So proactive SIMs do stuff. Mobile operators put all kinds of proactive features in your SIM. They talk to the network behind your back. Why do you care? The first reason is because lots of SIMs have buggy web browser apps. They have applets, Java code applets that are in the SIM that have known bugs that could be exploited. And there's a known example, a few years ago was a known example of something called SIMjacker, that they could send a specific SMS to your phone, and if you had the right type of SIMjacker would exploit a bug in one of the applets in your SIM to actually send proactive commands, to configure proactive commands that would then be picked up by your baseband processor and report information back to a control server somewhere. So SIMjacker is a known example. There are a few other examples, but this is one reason to care, because this can actually be exploited it can be exploited based on bugs in the Java applets that exist in some of these SIMs. Second reason we care is because governments own telcos. And if a government owns a telco, they can certainly convince or coerce or just demand that a telco put certain Java apps in a SIM. And those apps may sit latent until they've received a command, a properly formed SMS, for example, that's delivered to the SIM itself to activate or configure this feature, and then it becomes active. Are there known examples of this? No, there are not known examples of this. Is it likely that no one's done this before? No, it's not no. Almost certainly someone has done this before. It's too easy. It's too obvious. Once you understand how this stuff works, this is way too obvious. And the third reason we care is because this activity is completely undocumented. I mean, it took a month of badgering from an attorney. He finally threatened to drag them in front of a judge for contempt of court before they produced a witness who said absolutely as little as possible, just to give yes/no answers to our questions. Nobody wants to talk about this. Nobody in these companies wants to talk about this stuff. And it's interesting to know that your SIM is opening TCP/IP sessions behind your back that your baseband processor has no access to. And what is it doing? What's it doing? It's my SIM and my phone. I'd like to know what it's doing. So that's the other reason we should care. So we'll stop with an invitation. I have the equipment upstairs to do this. So if anyone has a SIM that they want to look at, and if you're going to be around tomorrow evening, send me an email to this address, and if there are enough people interested, we can arrange something. Also, if you happen to work, we can drop your SIM in the machine and see what happens. I didn't want to do it here. The demo gods are not smiling on me this week, so I didn't want to. I really didn't want to push my luck up here on the podium. But also, if you work with or know people who work with journalists or activists or attorneys or somebody like that, especially in a say a difficult regime somewhere, if you know people who work with folks like that, I'd really like to talk to them. I'm really interested in doing a real hunt for state actor exploitation of this stuff, and I'm not sure how to get that rolling yet. But if you know people who work in that area, like Amnesty International or something like that, Citizens Lab or something like that, I don't want to go introduce myself to them cold, but if I can have an introduction into it, would be nice. So that's the end of the presentation. Okay. Questions?
Are there questions?
Thank you. Do eSIMs have any role in this?
I don't think eSIMs have any special role in this, but I mean, all these features would exist in eSIMs. There's no reason to think that eSIMs don't have these same features in them. They're not. The eSIM question's orthogonal to this question. So.
Okay, but if we are talking about eSIMs, I have another question about eSIMs, if you know about them. So the software for the eSIMs has to be downloaded from the carrier when enabling the eSIM, right?
Yeah.
So would this make it easier to reverse engineer eSIMs rather than physical SIMs?
That's a very good question. I'd love to see that. The problem with that is that you have to with eSIMs, you have to physically remove the SIM from the. Mechanically, it's a little more complicated to do, but that's an excellent idea. So.
Any more questions?
In modern 5G systems, we know that in the SIM, you normally all the operators must to be hard code the public key of the network in order to encrypt the identifiers, in order to perform the authentication, so sushi identifier. Do you know where we can find some documentation? Because I think that they have created some API in order to modify, update during time this public key. Do you know where we can find some documentation, or you know how the vendors update these secret materials inside the SIM?
I haven't looked at this for 5G SIMs, but my best guess, if I were to try to do that, if you don't find it in the 3GPP specifications, which I don't think you will in the public specifications, is get them through the GSMA. They'd probably be in GSMA documents somewhere, but probably not publicly available. You actually need somebody as a GSMA member or find something that was leaked to get access to those. My guess is that this would be in GSMA operational documents where you would find that type of information.
Okay. Someone else? Okay, in this case,
Okay.
thank you.
Thank you.
Thank you.